Hello, everyone. Thank you for being here at the seminar. Today, we are pleased to have Cristina Martí, a PhD student from Climate and Physical Oceanography Group, and she will talk about energy transfer in the Mediterranean Sea.
Thank you. So, hi everyone, I'm Cristina, and I'm doing the PhD with Simon and Ananda. And today I'm going to explain a little bit what I've been doing this past year, that is working with energy and the concept of energy transfer in the Mediterranean Sea. And I'm using two different platforms. So I'm using in-situ data and then SWOT observations, and we're going to see the results. So first I'm going to introduce the concept of energy cascade in the ocean. And then I'm going to explain why we have this cascade with the balance and unbalanced motions. Then I'm going to talk about the first article I published, that is eddy splitting in the Balearic Sea with in-situ data. And then I'm going to introduce again SWOT and analyzing energy transfers with SWOT in the Mediterranean Sea. So the ocean is, we know it's multi-scale, meaning that we have different structures of different sizes. For example, here we have in the Balearic Sea these eddies that are, for example, smaller than this big gyre in the Algerian basin. So a question in physical oceanography is how is the energy distributed across these different scales? So here we refer as energy like kinetic energy, that is the movement of water, that is the square of the velocity field. So this has a theoretical framework that comes from the nonlinear momentum equation. This term, it's called nonlinear advection term. Then we have the velocity field multiplied by its derivative, and it's the responsible of describing how the flow carries and deforms itself and creates interactions between different motions. So we talk about cascading energy, and we have forward cascade, when energy flows from large to small scales. And then we have the inverse cascade, where the energy is flowing from smaller scales to large ones. So what happens in the ocean? Typically, we have that are mesoscale, that are of the order of 10 to 300 kilometers. Small eddies tend to merge and feed larger structures. However, if we look at the smaller structures as a mesoscale of the order of 10 kilometers, we see that large features strain and break into smaller ones. So we have a forward cascade, and this would be more or less the curve of energy flux in the ocean. So how we can explain this curve? We have different scales in the ocean that are defined by this number, that is the Rossby number. That is the ratio from inertial forces and Coriolis forces. So in the mesoscale, we have Rossby number typically of 0.1, meaning that Coriolis force is winning inertial forces. And then as we go smaller, we have some mesoscale that has Rossby numbers of the order of 1. So there's an interplay between inertial and Coriolis force. And this is the picture. From large scale to mesoscale, we have balance motions that govern the regime, typically geostrophic currents or eddies. And then passing to the mesoscale, we have more unbalanced motions that are geostrophic processes. And we have, for example, internal gravity waves, turbulence, or inertial oscillations. So we tried to look at all these concepts in this article that was published 2 weeks ago, that it's tracking an eddy splitting with in-situ data, and it was during the Calypso 2022 campaign. So here's more or less the outline. We have maybe you don't see well, this yellow line is a ship that went to this box that was a high resolution sampling that went over several times, and it captured an eddy splitting. So we used UCTD and ADCP data to track that. And we have first the eddy, which elongates. So we have here in the profile maps, we have this eddy here. Then this eddy is split it into two smaller eddies, and we can see them here, here and here. And then these eddies went away in the dissipation phase that are here and here. So with this, we ask what was the contribution of balanced and unbalanced motions in this system. So we used spectral methods, that if you want to know more, here's the reference. So we divided the water column in three stages, in 3 layers. So at the surface, at the mixed layer, we have dominance of balanced motions, meaning that this blue line is higher than the orange line. So in the y-axis, we see the amount of energy, and on the y-axis, we see the scale. Then as we go deeper, we see that the unbalanced motions have more importance, especially in the deep layer, where it crosses at small scales the balanced motions. So we have a mesoscale and mesoscale regime. We don't know exactly how to define it, but we can go further and also analyze the different phases of that eddy splitting. And we see that during the splitting phase, the Rossby number increases a lot. Here's the mean Rossby number as a function of depth for the 3 phases. So we have a more mesoscale regime. And the idea we talk in the article is that the strain intensification during that elongation of the eddy make the Rossby number increase that reaches order 1. So we have some mesoscale motions playing. And this triggers the cascade forward to smaller scales. And we also see internal wave activity, but if you want to see more, you have to read the article. So yeah, that's the first part of the talk where we use in-situ data. And we show that has high accuracy because we could track a lot of information from that eddy splitting, but it has limited spatial coverage, and we can't capture the 2-dimensional structure of the eddy. But we can ask, okay, we can use maybe conventional altimetry, but we have a problem that this was the conventional altimetry signal of that campaign, so we don't see nothing. But we can combine like the best of both worlds and use wide SWOT altimetry, that is the SWOT satellite. So for those who didn't know SWOT, it's a mission that was launched during December 2022 from NASA AGNES, and is sampling the sea surface height with a 2-dimensional structure at 2-kilometer resolution, that it's very high. And it enables that, for example, we can see structures like this. So here in the background, there's the conventional altimetry signal, and superimposed, we have the SWOT data that has more resolution, and we see also these internal waves. So we have better resolution. So now we have better resolution. We can go to the Mediterranean and track how is the submesoscale transfer there. And we looked at the 2-dimensional energy transfers down to 15 kilometers for the whole Mediterranean. Here I have an example of the 2-dimensional structure of these transfers of 2 passes near the Balearic Islands. So here red means forward and blue means inverse cascade. And we see that there's a lot of heterogeneity in the transfers. We don't have a clear signal of inverse or forward, but for instance, here there's an eddy, and we see a lot of transfers happening in the boundaries. So we can also take all the passes of the Mediterranean and make a time mean of these transfers, that is this curve here, and we see a clear seasonal cycle of that energy transfers. So this is quite new. We haven't seen that with other altimeters. So now we are here. I'm trying to understand why a little bit. And for example, here is, I don't know if you see it well, but here's the activity of the submesoscale transfers during summer. And this one is during winter. So we have a lot more variability. So yes, as a take-home messages, we think that submesoscale processes are key in the ocean energy cascade, but we need several techniques to observe them and observations. Then we see how the eddy splitting drives a breakdown of the geostrophic balance with in-situ data. And then for the first time, we can map energy transfers at small scale in the Mediterranean Sea with SWOT data. And we saw a forward and inverse cascade that coexist in space. And also that the cascade is not steady, that it has a clear seasonal cycle with a strong energy transfers in the winter. And that's all.
Questions for Cristina?
I have some questions. Let's see. Okay, I'm going to ask the questions regardless of whether they are stupid or not. So when you have the when you describe the splitting of the how do you call it, the gyre and eddy, right? When you describe the splitting of the eddy, you get I think a swing in the Rossby number during the splitting, and then it goes back after the splitting. Is that due to the fact that during the splitting you have a much longer let's say quote unquote object, and therefore maybe the Coriolis forces are more relevant because they will depend on the scale of the system, right? Meaning the original during the splitting, I imagine that the object has the elongation of the object is going to be larger than what the eddy was before. And is that the reason why you get this swing in the Rossby number?
So the reason mainly is that we have more divergent fields, and then this contributes to increasing of the Rossby number. But yeah, the idea is that so when the eddy splits, we have a very strong strain, but then as the eddies go away, like there's like again this equilibrium, like geostrophic again balance. So it's because of the high strain, I would say.
Okay.
Any questions?
Cristina, you could comment on the findings that we are obtaining with SWOT that are very new, so it's that you obtained less than a week or so. In relation with models, because there have been many numerical model studies in the past working with mesoscale. We didn't have enough observation, but they already saw something like that, right?
Yeah, but the problem with models is that they don't get that seasonal cycle. So they track, like if you look at one snapshot of transfer, for example, this one, maybe models do it well. But when you do a timing of the transfers, they don't get this seasonal cycle. And even high resolution model didn't get that seasonal cycle. But then if we look, for example, at eddy kinetic energy, we have it.
So the kinetic energy shows a seasonal cycle.
Yeah, with SWOT, with other altimeters, no.
The increase in eddy kinetic energy with models in this was something that was predicted.
Yeah, but not the transfer.
Of energy. This was really new.
Which models are you looking at?
The MIT model DM. Yeah.
What is that region?
No, not in any region. So.
Is this something that is peculiar to the Mediterranean, or maybe this region of the Mediterranean, or is something that you observe?
No, there's an article talking about the Atlantic, North Atlantic, like they have moorings, and they see also the seasonal cycle, and when they look at high resolution models, they don't get it. So it's a problem in general with models. Yeah, we won't have.
And for this scale, you only have inverse cascade during the whole.
That's curious because when you look at the spatial snapshot, you see forward cascade.
So did you see if it was localized in a specific place, and you have
maybe I think
a
this
big
is
transfer
not-
in
yeah.
site,
I
or
mean, it's not. I don't see it clearly here, but in Algorand, for example, there's like a big signal of forward transfer here. That it's like more stationary than the other places, but it's a bit messy. It's not clear.
So how do you measure this from the data? How do you
So
estimate this from the data?
this in particular, or
One of these points, right? So this is the
Yeah.
energy transfer. How do you measure the energy transfer?
so here it's a technique called coarse graining
Mhm.
that you use like a filter.
Mhm.
So you set the scale, you filter the motion, and then you see if the energy is going to the smaller scale or the higher scale, and then you assign the transfer. But mathematically is the strain tension multiplied by the momentum flux.
So the data you have velocity, you are.
Yeah, yeah,
You
yeah,
have
so
UIB
velocity.
from the satellite.
Uh-huh.
And I think that the satellite will have much higher resolution than before, so we're seeing scale that we couldn't see.
Sure.
So those UMV, and from the UMV, you can do all.
But a transfer means something, a process that happens in time, right? So, no, or you can just from a snapshot decide where the
The
thing is
transfer
going.
in scales.
Yeah,
Scales.
it's a special scale, this, yeah. It's not in time,
So how do you know that the energy is moving from one scale to another scale?
because you filter the scales.
I mean, you can determine, that's the thing I don't understand.
So for example, imagine.
I'm sorry if I'm asking stupid, but you,
Okay,
you have,
so-
you can assign, I can understand that you can assign a power to each
Yeah.
scale, that's fine. But the transfer means a process that happens in time. Right,
Yeah.
meaning that you have a certain energy here that moves into another scale.
Yeah,
So how do you estimate that from, if you only have a single snapshot?
so that's the temporal view of the energy transfer, but then you have like, for example, you see this eddy here. So this snapshot is from one scale in particular, so it's 25 kilometers. What I did is, okay, this eddy is bigger than 25 kilometers. So this signal is assigned to higher scales than 25. So you can see that you have the field at 25 scale and then the field of bigger scales than 25. And you said if the energy of the scales of 25 is bigger than the energy
So
of
it's a
higher scales.
comparison of energy, but you don't,
Yeah.
you're not, I mean, is there a physical reason why you should have a transfer of energy?
It's by the momentum.
No,
this
that's, okay,
drives
sorry,
the
my
transfer.
question was, there was no what was. What I mean is, you could, for example, have a process where this is always there, meaning you always have the same power spectral density, right? In time, this doesn't mean that there is an energy transfer between that scale and that scale. You understand what I mean?
No,
In order to have a transfer means I'm moving,
yeah,
I'm dissipating my energy into on my scale into your scale.
Yeah.
Right? And that means that left by myself, I guess I would dissipate and you give all the energy to your scale. If I only have a single snapshot, I could, for example, have a situation where I'm always at this energy and you're always at that energy.
Mhm.
And there is no transfer between us, but
Yeah.
then the power spectral density is the same. And how do you know that there is actually a transfer of energy? Does it make sense what I'm trying to say?
yeah, yeah. So for a single snapshot, you make a curve of the energy.
Fantastic, yeah.
And you see, for example, at 15 kilometers, the energy is higher than at 25. So you say that the energy is flowing to 50
Now is the
kilometers.
flowing that I don't understand.
Like the energy is concentrating at 50 kilometers. So when you are at 25, you see, okay, I'm forming bigger structures at 15 kilometers. There's a bigger structure than me forming, so I'm doing inverse transfer to that structure. No,
I don't want to hold the conversation, so.
Yeah.
I'll ask you a little bit more.
okay.
Maybe in your in the slope of the spectrum, minus
Yeah,
3
maybe.
or minus 5/3, that then all the energy transfer.
Yeah. So this is the power spectrum. Yeah. So
I'm fine with the power spectrum.
yeah. So I'm looking, for example, at 10 kilometers here. The energy is higher than at 5. So the energy, I say that at 5 kilometers we have inverse transfer to 10. Because the energy is higher here.
Have you answered my question?
Yeah. But he said maybe.
My
it's
question
very-
is that-
Yeah.
Sorry, I didn't get you.
What's healthy?
I was thinking, I didn't. Okay, then,
Repeat it again or not?
and if, maybe we can.
Yeah, okay.
No, it's.
So all of this is in the geostrophic quadrant. So what about the transfer from geostrophic mesoscale to geostrophic submesoscale? That's something that's not considered here, or?
Here, for example, in this case of in-situ data and eddy splitting, it's considered because we have the ADCP field. But in, yeah, and I decompose it with this, with the spectral thing. And here I only have geostrophic velocities, so it's only geostrophic. But I'm trying to do it with cyclogeostrophic correction, but it's in progress. But yeah, that's all geostrophic.
More doubt?
Yeah, because in the spectra, you also separated geostrophic and the geostrophic and you.
Yeah, balanced is related to rotational.
Yeah.
Yeah.
Well, that's it. Thank you, Cristina.
Thank you.